Good day, everyone, and welcome to our webinar on flue gas analyzers for safe combustion of high hydrogen fuels, which will be presented by Tim Talon. My name is John Kearney, and I lead the product management team at AMETEK Process Instruments, and I'll be serving as the moderator for today's session. We are excited to share some interesting and hopefully educational information on trends in global decarbonization that are driving the use of hydrogen and high hydrogen fuels, talk about some risks in using these fuels, and ultimately the role of flue gas measurements for combustion safety and process control. Before I turn the presentation over to Tim to introduce himself and share his content, I just want to go over a few logistic items with everyone. We are recording the session, so to minimize the background noise, just ask that you please mute your phone or computer mic. We do want the session to be interactive, so if you do have a question or a point to discuss, please use the chat feature. For those that might not be familiar with the Microsoft Teams platform, you'll see an icon on the top right area of your screen that looks like a quotation mark. If you click on that, the chat box will appear on the right-hand side, and you can feel free to type your questions there. I'll either interrupt Tim during the presentation to address that question, or we'll save them to the end. If we don't get to your question during the session, Tim or I will respond to you via email after the session. As I mentioned, this webinar is being recorded, and it will be available on our YouTube page in the coming days, and that link is also posted in the chat. This webinar, of course, is sponsored by AMETEK Process Instruments. We are a worldwide manufacturer of process analyzers and instrumentation, and we serve a wide range of markets from environmental monitoring to hydrocarbon processing, including things like refining and petrochemicals, as well as power generation, natural gas, and several others. All of our engineering and manufacturing activities take place in several North American facilities, but we serve our customer base through a network of direct sales and service offices throughout the world, including direct AMETEK employees, as well as factory-trained manufacturers, representatives, and distributors. So we're local to serve all of our customers. So with that, Tim, I will turn the presentation over to you.
Thank you, John. Good morning, good afternoon, good evening. Thank you for joining us today. In this specific talk, we're going to talk about flue gas analyzers and how they can ensure safe combustion for pure hydrogen and for high hydrogen fuels. So in this presentation, we will dive into the explicit role of flue gas measurements and how they affect high hydrogen fuels. We'll talk about decarbonization, about some of the properties of hydrogen which make it unique and how it impacts risks and has different implications on the combustion process. We'll also talk about the three critical roles of flue gas monitoring, especially in combustion. And we'll talk about how catalytic detectors can detect unsafe conditions, especially as it's primed very well for hydrogen detection. And we'll talk about those key flue gas measurements. And as John mentioned, there will be time at the end for Q&A, or also feel free to submit your questions in the chat below, and we can get to that during the presentation. So to start off, let's talk about decarbonization. So there's an inherent move towards decarbonizing combustion processes in industry in general. Governments have signed a lot of net zero carbon emission policies. There's a big focus on climate control and reducing greenhouse emissions, and that is particularly the case around carbon dioxide. And a lot of industries in the midst of it still require combustion. I mean, combustion generates carbon dioxide, but a lot of industries still depend on that. And that includes hard to decarbonize industries such as steel, cement, and chemicals, but also things like mobility in vehicles and ships and transportation. So there is still a heavy dependence on combustion and combustion-related processes. When we think about like large-scale decarbonization around combustion specifically, there's three methods that come up pretty commonly. There's the carbon capture method. There's different carbon capture methods, but carbon capture to remove carbon emissions from the combustion process itself. There's also electrification to generate heat in place of combustion, so using electricity so that you don't have to rely on the combustion process. And there's also the use of hydrogen, which does not have any carbon atoms. So using hydrogen as a fuel to generate heat without carbon emissions. So that's another option as well. And so when you look at it, combustion remains important for our future, but it's also moving towards decarbonization. So we have to think about how are we going to decarbonize our processes. So let's talk about those three methods: the carbon capture, electrification, and hydrogen. So when we think about carbon capture, whether that be pre-combustion, post-combustion, or oxy-fuel carbon capture. However you choose to remove carbon dioxide from the combustion process, it's pretty well suited for certain applications. Um, Carbon capture is much more economical, especially on the grand scale when you have a singular process or a singular pipe flow that holds a large amount of the carbon dioxide. So things like blue hydrogen production, where or autothermal reforming or partial oxidation or steam methane reforming, different processes that generate syngas can use carbon capture very well because much of the process stream is consolidated, and that centralized singular source can be sent to the treatment to the downstream carbon capture system for treatment and removal of the CO2. So it's pretty well suited for large scale systems and centralized emission sources, but it becomes more of a challenge, especially when you look at flue gas carbon capture, where some plants have many different carbon point sources, combustion point sources, where it would take a lot to revert all those stacks to a common duct and then use low pressure carbon capture methods to remove the CO2. All of that tends to be much more costly for those types of carbon capture methods for flue gas, and it can require a significant amount of equipment for those processes. So that's just the view on carbon capture. When it comes to electrification, it's very well suited when you have a greenfield plant where you have you can buy new vessels and you can pretty much buy from a clean slate. And it's also very well suited for low temperature applications where it's not super energy heavy and you can use external power sources in order to supply that energy. But electrification become more of a challenge, especially when the economics factor in when you're trying to retrofit an existing plant. And say you have multiple heaters or multiple combustion sources, you may not be able to target every one of those vessels and buy all new equipment that's electrified. So that can be more of a challenge. And there's also a dependence on external power sources. You're still going to need some type of electricity in order to generate the heat. And so that can be much more of a challenge for high temperature applications. So electrification has its place in the realm of decarbonization, but it can be more of a challenge for existing plants around combustion. And then for hydrogen fuels tend to be much more versatile. It's sort of agnostic whether or not it's a centralized combustion source or it's small dispersed combustion sources and furnaces. So much more flexibility there because you're just basically changing the fuel from what may be natural gas or oil to hydrogen or a hydrogen blend. So it's much more versatile from that respect. And it has much less of an impact at the combustion source. I mean, there may be considerations. It would be prudent to get an evaluation to see how your burner can handle hydrogen fuels, but outside of changing maybe the burner and some piping, it has much less of an impact at the combustion source itself. You're not installing large amounts of carbon capture systems, for example, large towers or absorber towers, or changing the entire vessel to be electrified. So it has much less of an impact on the combustion source itself. And then there's also that has less plot space requirements. Like I said, there's no major absorber tower to accommodate within your plant. And the other thing to realize is that hydrogen fuels are not new. They're actually used as a byproduct fuel in many industries. And one case that comes out pretty often is refinery fuel gas in refineries. Some refinery fuel gases can contain up to 70% hydrogen. So it's not a new thing, and for some industries it's pretty common already. So when it comes to like hydrogen as a fuel source, it certainly offers the most versatility for existing combustion processes. Now let's take a look at combustion. Let's think about combustion and let's talk about specifically how does the hydrogen molecule compare to the methane molecule? So we can first talk about the physical properties and then we can kind of go into the combustion properties. So on the physical property side, one of the most notable things is just the fact that hydrogen is much smaller. I mean, it's 8 times less mass compared to methane. And as a result, it's also much lighter. The density is much less. It's 8 times less dense compared to methane. So already you have this very small and very light particle in your fuel source. So that's some differences already. And then also, because hydrogen is a small molecule at the same temperature compared to methane, it actually moves 3 times faster compared to methane. So it's even more a fast-moving molecule compared to methane at the same temperature. And beyond that, it has a much wider range of flammability. I mean, the flammability of hydrogen is considerably higher compared to methane, from 4 to 75% compared to methane. Methane's window of about 0 to methane's window from 5 to 15% by volume. So ultimately, when we look at hydrogen, it's 8 times lighter, almost 3.5 times faster diffusing compared to methane, and it's much more flammable. So when we think about designing our combustion system and adding high hydrogen fuels and high hydrogen fuel blends, there's something to consider here for the differences. So that's just the physical properties. Now let's talk about combustion properties. Now, hydrogen's unique because it's such a small molecule, but it also contains a lot of potential energy. So when we look at it from a volumetric basis, because it's so small, you're going to need 3 times more volume of methane, or 3 times more volume of hydrogen in order to meet the same heat release that you have with methane. So if you currently have your fuel flow having a volumetric flow monitoring system, you would anticipate needing 3 times more hydrogen in order to get the same amount of heat release as what you might be using with methane right now. So if you use it on a volumetric basis, if you measure flow on a volumetric basis, you're going to need 3 times more flow in order to match the heat release of methane. But on the flip side, if you monitor mass flow of your fuel, you'll need about a third less. You'll need about a third of what you currently have as a mass flow for methane for the same heat release. So it's pretty important to be mindful about whether or not you're going to be measuring flow on a mass basis or on a volumetric flow basis, because that has different implications for what you anticipate when using hydrogen as a pure fuel source. Now, beyond that, hydrogen also has a much faster flame speed. It's 10 times faster compared to methane. And so if you use a premix burner, for example, you could have a potential issue of flashback because those hydrogen flames will consume the oxygen as fast as possible. It is much more prone to flashback because of that faster flame speed. And then beyond that, it also burns hotter, so slightly hotter, but hydrogen flames burn slightly hotter compared to methane. So something to be mindful of, especially if you have certain metal around your burners. And then on an ignition temperature basis, hydrogen is similar to methane, but still it requires less temperature to react compared to methane. And then finally, less energy is needed to ignite hydrogen compared to methane. And it's not just a little bit less energy, it's 10 times less energy to ignite hydrogen over methane. So something to be aware of is obviously it's much more prone to sparking and much more prone to ignition because of its much lower ignition threshold, because it's a much smaller molecule as well. So ultimately, just takeaways on the combustion properties of hydrogen is that it's 10 times faster on a flame speed basis. It burns hotter, and also it's important to consider those differences in heating values, whether it's on a mass basis or on a flow basis. So pulling that together, some other implications of using hydrogen versus methane is that there's less air requirements. If you were to just design the combustion reaction around the same heat release, you would actually need 20% less air compared to methane. And so if you have a high hydrogen fuel blend and then you go to pure oxygen, or if you have a high hydrogen fuel blend and then go to pure hydrogen, you have to be mindful of that you have the right amount of air, because hydrogen by itself would need less air compared to a methane fuel or a mixed fuel. So it's important to give some margin, especially if you're going to have potential swings in the composition of your fuel gas. So something to be mindful of there is that hydrogen by itself needs less air, but if you have a mixture of hydrogen and methane or hydrogen some other compounds, you're going to have more air as a buffer in order to handle that high hydrogen fuel. And then on a potential NOx emission basis, because hydrogen moves faster, it burns hotter, those potential hotspots create more potential NOx. So that is something to be mindful of to monitor NOx or NOx levels or NOx requirements, because depending on how the air is staged at your burner could dictate how you could dictate how much more NOx you should see. So there is a potential risk of having high NOx emissions or higher NOx emissions. So if we kind of list those potential risks of hydrogen, distilling out what we talked about from the property side, hydrogen firing or high hydrogen fuel firing shows a potential risk of flashback, especially in premix burners. So that's something to be aware of. It does show the potential risk of higher thermal NOx production because of those hotter flame temperatures and because of that faster flame speed, smaller flame size, more potential pockets for higher temperatures, which generate higher NOx. And that could also impact permits too, especially if your permits on a ppm level basis, because you're changing that could also change impact you on a permit basis because you're generating water and you're converting your permits to a dry basis. So that's something else to be mindful of as well. Other risks, because of the high temperature, certain firebox geometries may have higher radiant heat directed towards the tubes. So higher temperatures at the tubes might be something to monitor the tube temperature. And then also a potential risk of overheating near the burner and other metal pieces. So it is important to think about what metal parts are exposed, whether that be like a flame rod or other types of metal pieces around the burner, and considering either increasing the thickness of that metal or have a different type of metal to dissipate the heat and be able to handle that exposure to hydrogen and hydrogen combustion. And the last potential risk, it's always a potential risk around the combustion process, but it's the risk of an accumulation of a combustible or fuel-rich mixture. And while hydrogen is highly reactive, it does have a high flame speed, it is very fast diffusing. If you have a swinging composition from, say you use methane and then you use a methane hydrogen mixture, if there is some type of potential loss of flame you could accumulate a risk. You have the risk of accumulating a combustible mixture, and flue gas monitoring can help with monitoring for that. In addition, because hydrogen uses less combustion air compared to methane, it would also be prudent to have some type of safety margin installed in what excess air levels you're using. So when we talk about flue gas monitoring, the next half of this presentation, flue gas monitoring focuses primarily on this last risk around hydrogen firing. And this is really where flue gas analysis plays a pretty important role in increasing safety and also reducing risk. So now let's talk about the three critical roles of flue gas monitoring. So flue gas monitoring has three important roles. The first role is the role of the operational set point, and I'll get into that in a second. The second role is the role of optimization, so fuel efficiency, and the third role is safety. So when we talk about the operational set point, the flue gas analyzers such as like a zirconium oxide detector measure oxygen on an excess oxygen basis. And that excess oxygen reading represents the oxygen after all combustible content is consumed. So if there was any chance that there was a combustible cloud or methane, the excess oxygen reading would first consume all of that combustible content on the sensor itself, and then the remaining residual oxygen would be measured afterwards. So the excess oxygen measurement is important because it correlates directly to the air to fuel ratio at the burner. So if you have a low excess oxygen level, you can increase the air, and that would air to the burner, and that would increase your operational excess oxygen set point. And as I said, it ensures that you have sufficient air provided at the burner with a safety margin so that you're not running at a jagged edge of stoichiometric conditions and potentially unsafe conditions. So let's talk about the importance of the excess oxygen measurement. And so this is a typical, very general combustion process. You can see that there's a burner. You can see that there's a combustion air blower providing combustion air. And typically, in the simplest sense of this type of combustion setup, the temperature measurement can be used to fire the fuel and to monitor the fuel level. But then it's the excess oxygen reading at the stack or in the flue gas that drives the opening of secondary air to the combustion process. So with the excess oxygen measurement, it controls the secondary air and ensures that you have the sufficient air to fuel ratio at the burner so that you're not running too lean to create a potentially fuel rich and unsafe condition. Now, this is just a generalized furnace type setup, but say you had like a fired heater, for example. This is a much busier slide, but in the same way at the flue gas, the excess oxygen measurement is taken, it's trimmed, and that informs the air that you drive to the burner. So in either case, the excess oxygen measurement provides that secondary control, that operational set point, to ensure that you have sufficient air at the burner and a correct amount of air, air versus fuel for safe combustion. So that's the first important thing. And then it's important to realize, like, what's the optimal excess oxygen level? Because your set point depends greatly on the fuel that you're using. And you could have many different fluctuations based off of the mixing characteristics within the burner, based off of variable load and content of the fuel itself, especially if you switch between two fuels at a given time. It could also be impacted by humidity and density. So there's really no fixed value. So how do you know what's optimal? And that's where the second role of flue gas monitoring comes in. And that's the role of optimization. So optimization means that you monitor the health of the combustion process through what we call a combustibles measurement. And combustibles is effectively carbon monoxide and hydrogen. So if you had a high hydrogen fuel, that would have some type of hydrocarbon content and some amount of hydrogen. The combustibles measurement would monitor for the unburnt carbon monoxide and any incomplete combustion due to hydrogen would also be detected. And so just to kind of put that into a reaction type state, if you were to use a high hydrogen fuel that has methane, for example, that methane molecule would first be consumed into ppm levels of carbon monoxide and hydrogen, and then only if there's enough oxygen present would that carbon monoxide and hydrogen convert further to produce CO2 and water. And again, that's in the case of a high hydrogen fuel, for example. If you had just pure hydrogen, then you may have ppm levels of hydrogen that you could monitor. And then if you had spikes in hydrogen, you could effectively detect a flame out. So let's talk about that role of optimization before we get into the safety element. So when we talk about operating an excess oxygen measurement, as you increase your excess oxygen set point over time, you are running a little bit more and more less efficient, because at stoichiometric conditions, you could say that's 0% excess oxygen. That would be like the ideal scenario. But what happens is you need a little bit of a safety margin. But as you go too far, beyond 1%, beyond 2%, beyond 3%, you have increasing losses of efficiency because you're effectively burning more fuel in order to burn more air, in order to heat more air at the outlet. So there's an efficiency loss by operating too high of an excess air level. But on the flip side, when you monitor combustibles, you have a potential risk of what they call combustibles breakthrough. So at some point, getting close to stoichiometric conditions of 0% excess oxygen, you have this risk of a significant spike in combustibles. And so by overlaying these two graphs in a hypothetical but very real way, you can go from what is once a operational set point to an optimal point. And so, as I mentioned, measuring oxygen by itself provides that operational set point. And that's the most important first step of any type of oxygen flue gas monitor, is that operational set point for the burner. But from there, that combustible measurement minimizes that loss of efficiency so that you have that you lower your excess air levels, which means that you have less fuel consumption, and you also monitor for any potential unsafe condition beyond this breakthrough point. So from a optimization standpoint, there is a very real secondary reference point that combustibles plays in order to have an optimized combustion process, what we call optimized combustion. And the third most critical role of flue gas analysis is the role of safety. And safety can come in the form of ppm level measurements for combustibles to make sure that you detect the onset of incomplete combustion, to make sure that you can detect incomplete combustion and monitor for combustibles breakthrough. But then also the role of detecting percent level measurements of hydrogen and hydrocarbons from things that may be like a fuel leak or a loss of flame. And so when we talk first about the incomplete combustion, as I showed you this graph before, a combustible detector can alert you for carbon monoxide breakthrough. So if you're using a high hydrogen fuel, you can detect that carbon monoxide breakthrough. And so that combustible breakthrough can be detected using that combustibles measurement. And then when we look at the hydrocarbon detector, we look for things like flame out. So fuel leaks could happen because of a degraded burner tip, causing too much fuel to enter into the system, or potential flame out because the burner air nozzle was plugging. So there's too little air. But in either case, a hydrocarbon detector can be used in order to detect those percent level measurements of methane and hydrocarbon, and in this case, even hydrogen. So hydrocarbon detectors provide that extra level of visibility for high percent levels. And this is also the case for startup, especially while you get permissions for light off, but also for operation. We have had customers who have detected high levels of hydrogen in their process, and they were able to detect it early because they had a methane or hydrocarbons detector to monitor for that. Now let's talk about the specific catalytic nature of these methane and hydrocarbon detectors. So catalytic detectors are used for both methane monitoring and also for combustibles monitoring and for hydrocarbon monitoring. And all of them can be used for hydrogen because hydrogen is very reactive within the similar zone of both of them. So there are two different types of catalytic detectors that we use and that we see in industry. The first one is a RTD type detector. You can see that on the right over here with those two RTD elements. And there's also what we call a catalytic bead or hot wire type design. That's demonstrated below from this trigger photo right here. Now, in both cases, both detector types use an active and a reference element. So one is coated with catalyst, the other one is not. And based off of how the combustibles oxidize on the catalytic element versus the reference, it's able to make a measurement. And each of these measurements use the available oxygen in the flue gas, in order to oxidize the sample and make a measurement. But what's unique about these detectors is that they are tuned for a particular zone of reactivity. So, for example, our combustibles detector is able to measure carbon monoxide. It's also able to measure ppm levels of hydrogen. And if there were any compounds within that band of zone of reactivity, they could be detected. Those catalytic detectors are able to make an umbrella, what I call an umbrella measurement. So it's able to cover all both carbon monoxide, but also hydrogen. And that zone of reactivity is best measured and calibrated with calibration gases, obviously. But that zone of reactivity is also not speciated. So it very much depends on whatever reacts within that zone it'll pick up. But as I mentioned, our combustible detector is designed to measure carbon monoxide and hydrogen. And then our methane detectors are designed to monitor for hydrocarbons and methane, but they can also detect percent levels of hydrogen because hydrogen is similarly reactive to hydrogen. It's similarly reactive to methane and other hydrocarbons. So for certain designs, we use our hot wire detector. So the hot wire detector we use for the methane measurement, and we also use it for high sulfur combustibles measurements. But it's the fact that these catalytic elements are non-speciated that they give you that flexibility of monitoring a wide range of compounds. And as I mentioned, because hydrogen is more reactive, catalytic detectors are also more sensitive to them, sensitive to hydrogen. So combustible detector will pick up hydrogen just as much as a methane detector will pick up hydrogen as well because they're catalytic in nature and because hydrogen is reactive in a similar way. So that's an important thing to consider. Now, when it comes to the threefold rule of flue gas analysis, as I said, it comes back down to the operational set point for the proper air to fuel ratio at the burner. It comes down to optimization for the secondary reference point to make sure that you have the optimal level of excess air where it's not too high but not too low. And also the role of safety, monitoring for ppm levels of incomplete combustion, but also for potential loss of flame or fuel leaks. So when it comes down to the flue gas measurements for pure hydrogen, you can use the excess oxygen measurement for safe operation. As I said, that's a primary indicator to make sure that you have a sufficient safety margin that you have enough air to fully consume any amount of fuel in the gas in the flue gas, but also to make sure that you have a good operating range for your process. So the excess oxygen measurement is important for that reason for safe operation. A combustible detector can be used to monitor for ppm levels of hydrogen, and that can be important for safety, especially if you are running very low excess oxygen levels. And it also provides a secondary reference point just to make sure that you're not operating too low where you have high ppm levels of hydrogen, for example. And then it's also important to have a percent level hydrogen measurement for safety in the case of loss of flame or fuel leak or light off. And even in some cases, different processes use methane to light off on. So by having a hydrocarbon detector to monitor for percent level of hydrogen, you can also monitor for percent levels of hydrocarbons and provide an extra safeguard for safety during light off and purge cycle. So those are the three important measurements for flue gas monitoring for pure hydrogen for safe combustion. And then when it comes down to high hydrogen blends, you again have that excess oxygen measurement for safe operation, or that operational set point for the air to fuel ratio. You also have the combustible measurement for efficiency and safety, especially if you have a high hydrogen fuel blend. There are going to be some amount of hydrocarbons present, so that hydrocarbon will first oxidize into carbon monoxide, and then over time it'll fully oxidize to carbon dioxide. But by having that combustible measurement, you can safely monitor for combustibles breakthrough. And you also have that secondary point for optimization, like I said. So that's important, especially if you're considering a high hydrogen fuel blend for optimization. And then when it comes down to hydrocarbons, as I said, the hydrocarbon detector that we provided for methane measurements, for hydrocarbon measurements, can also be used for hydrogen. So that provides safety for fuel leaks, to monitor for fuel leaks, for light off, and also any potential process tube leaks as well. So say you have a fired heater, for example, you can monitor for a potential tube leak as well, because the hydrocarbons detector can pick up on not just one hydrocarbon, but multiple hydrocarbons, in addition to hydrogen itself as a fuel. So I know that was a lot, and I hope that was insightful for you. Let's just summarize everything that we talked about, just so we're all on the same page for the key takeaways. So as I mentioned, hydrogen offers a great versatility when it comes to the existing install base of combustion processes to reduce carbon dioxide emissions. And it's especially important for those small dispersed plants that want to reduce their carbon footprint. Because hydrogen is a fuel, there's no need for additional towers or absorber infrastructure in order to support that hydrogen fuel. So that's the first takeaway. The second one is, again, the realization that hydrogen is so light that it is very fast diffusing. It's not very dense, so it's very fast moving, it's very diffusive, and it's also more flammable. So it's important to keep that in mind, especially as you transition from what may be a traditional fuel to a hydrogen or high hydrogen blend. And then for hydrogen flames, again, from a combustion property standpoint, they're 10 times faster. So they burn hotter, they have different heating values, as I said, between mass flow versus volumetric flow. So it's important to realize that there is a potential risk of flashback, especially for premix burners, or if you have wide swings in composition. So if you have a wide swing from, say you go from operating with hydrogen and then you go to methane, you want to make sure you have the right amount of oxygen so that you don't have a potential risk of flashback because you switched from one fuel to the other, or because you introduce a fuel blend at some point. So that's important to keep in mind. And there's also the potential risk of higher thermal NOx emissions. The other important takeaways is the fact that flue gas analysis and flue gas analyzers provide a critical role in combustion safety and combustion operation. And that's through the role that it plays in the combustion set point, so the operational set point of the air to fuel ratio, the role of optimization to allow you to lower the excess oxygen levels for safety, or within a safe level for fuel efficiency and to reduce emissions. And there's also the role of safety to monitor for carbon monoxide through combustibles breakthrough, through incomplete combustion, through ppm level measurements, and then also through safety of monitoring for a loss of flame or a fuel leak or something like that. So flue gas analysis does play an important role for combustion processes in these three ways. And then finally, it's important to realize that those catalytic detectors, they're not speciated. They do provide that umbrella measurement so that you can monitor for ppm levels of carbon monoxide and hydrogen in the form of combustibles. And that you can also monitor for percent levels of hydrocarbons, which include hydrogen because it's similarly reactive to the hydrocarbons. So in either case, hydrocarbon detector provides you that flexibility for that hydrocarbon detector, the catalytic detectors. The catalytic detectors themselves provide that flexibility for monitoring that range of compounds in that reactive zone, and that allows you to monitor for hydrogen by itself or hydrogen in some other compound. So with that, I know it's a lot to take in, but we do have time for questions, so feel free to raise your hand or submit a question in the chat.
Hey, Tim, thanks for that. There are a couple of questions in the chat. The first one came in when you were on slide 55 talking about the catalytic detectors. And this is a longer question. I'll read it, Tim, and then we can talk through it. But It says when using methane, we measure the CO, and realizing that COE sensors measure both CO and hydrogen. How to relate the value from the sensor when a combined hydrogen and methane gas is used, especially when the hydrogen uses less air. So for example, in the question, for example, with methane, let's say the CO level may be 400 ppm. What value would we be looking at with 20% hydrogen added to the methane?
That's a great question, John. I'll take that in pieces, and if I didn't cover anything, please fill me in on the next half of the question. The first thing I want to point out is that, from what I heard, is that the methane detector, the combustible detector is designed for that range of carbon monoxide and hydrogen. Combustible detectors are not operated hot enough, especially are not operated hot enough in order to crack methane, which is why you need a hydrocarbon or a methane detector in order to monitor for those higher, in order to crack methane effectively. So just to be clear, combustible detector would be able to monitor carbon monoxide, would be able to monitor hydrogen. Combustible detector would not be able to measure for methane, just because it doesn't operate hot enough to crack methane and also accurately monitor for ppm levels of carbon monoxide. So that's the first half of the question on carbon monoxide versus methane. But could you fill me in on the next question, John, and then we'll kind of take it into pieces.
Yeah, so the example that was offered on the back half was, for example, methane, and then there's a hyphen, so I'm assuming with methane gas, CO may be 400 ppm, and then what value would we be looking at if you blended 20% hydrogen with the methane? I think, and the question I think is what value would the CO go to in that situation where you're now starting to blend hydrogen with methane, and what would the catalytic detector look like then? What would the measurement look like?
Right. So I don't want to be misleading. It really does depend. It really depends on the burner mixing properties, and depends on the flow. But what I will say is that, from an intuition standpoint, there would be some proportional reduction. It's hard to say what ppm level of hydrogen you would remain if you had 0% methane. If you had 100% hydrogen, it's hard to say what would be the ppm level measurement of hydrogen, because it's very dependent on where did you locate the flue gas analyzer, what forms of air ingress is there in it. But from that standpoint, there is some intuition that if you had 20% methane, or excuse me, 20% hydrogen in your fuel, that you would potentially have some offset of that. So it could be between, I think, 10 and 20%. But it is hard to judge that because it's very dependent on many other factors in addition to just the fuel composition itself. Does that answer your question, John?
Yeah, no, that's good, Tim. Thank you.
Yeah, that's a good question.
Second question from a different person here on the catalytic detector measurement. There's two questions here. I'll give you the first one here. Are catalytic detectors fast enough to be used as part of a safety loop?
Okay, that's also a very great question. It sort of depends on what are the requirements of the safety loop. So sometimes I hear that the measurement should be made in less than 30 seconds. In other cases, it should be less than a minute. In some cases, it's also less than 90 seconds. In some cases, it depends on the reactive time between the valve shuts off to the point of detection, and 2 minutes might be enough. So like that, it's a little hard to say that, but from the standpoint of combustible detectors, so RT detectors are a little bit thermally larger, so they may have a couple second additional offset compared to a hot wire detector. But in the case of high hydrogen fuels, hydrogen is more reactive, so there'd be less time to catalyze. The hydrogen, because the hydrogen is so reactive. So it would be able to pick up on hydrogen if there was a suitable, if there was a certain amount of hydrogen in the flue gas for it to be detected. So it's a little hard to say, John, for this the safety loop, just because in some cases it really depends on the response time requirements. But in other cases, it can be used for monitoring for the onset of unsafe conditions. It has been used for the monitoring for safety. And when it comes to like safety systems, it really depends on what's the criteria for the SIS system or the safety system. So I know it's another depends answer, but it's certainly something that if you'd like to reach out and talk further, feel free to reach out so that we can evaluate your application specifically and see what are the needs of your response time, and also is there high particulate, in which case there would be like a filter, or are you able to handle higher levels of aspiration. So there's different things that we could consider, especially if response time is a criteria for your safety monitoring. But it sort of depends, and it's application specific, but like there would be things that you could do in order to increase the speed if you needed to, because the element itself is fast. It's just anything before that, the sample system, the time it takes to get from the burner to the flue gas to the measurement point, all that takes time. So that's why I bring in a lot of factors as to where is it located? Is it located in the radiant section, the convection section? Are there tubes around it? Are there different things that would pose obstacles for the sample? Because when we talk about safety, we want to go into those details because safety requires that whole picture thinking. So,
And the second part of that question was really
Sure.
sort of compare and contrast maybe other technologies. So
Sure.
this one related to tunable diode laser technology, and whether maybe you could just compare and contrast sort of the trade-offs of a TDL. And I would assume this is around the combustible measurement, since it's with that question, but maybe just compare and contrast some of the trade-offs between the point measurement with this versus the path measurement that I guess TDL would bring. But the second question was around TDL advantages. So maybe just compare and contrast the technology types a little bit.
Right. So one of the advantages of the combustibles detector in the catalytic type detectors is because it is the advantage of that zone of reactivity. Because if you have a high hydrogen fuel blend, you could have carbon monoxide, you could have hydrogen, you could have some amount of incomplete combustion, and you could also have a potential fuel leak and need to monitor for methane or whatever else might be in whatever type of other hydrocarbons are present. So there is an advantage of being able to have more visibility on what has, what level of incomplete combustion, what level of flame out have you, what potential like flame outs you might have in those cases. So there is the advantage there. Where tunable diode lasers kind of come in is the realm of having a very specific speciated measurement. So if there's a very specific measurement that they're looking for reporting sake, like reporting the precise amount of carbon monoxide, that would be one way to monitor it. But if you vary fuels and use pure hydrogen, a carbon monoxide laser would not be able to pick up on that hydrocarbon, or the hydrogen. So the tunable diode laser certainly helps when you want a very speciated measurement, a very specific measurement for a very specific compound. Or in the case of carbon monoxide and methane, you could monitor for both of those. But if you're looking at having, if you're looking for a safety measure, if you're looking at it as like a safety measurement or a way to monitor for that incomplete combustion range with flexibility, a catalytic detector does offer more flexibility for that because of that non-speciated nature, that umbrella measurement. So it's different ways of looking at it because both technologies exist for a reason and they have their advantages, but it really depends on what's the case for high hydrogen fuels. And for high hydrogen fuels, sometimes you need flexibility. What's the case for hydrogen? Sometimes you need sometimes you need flexibility on. Sometimes you need visibility instead of flexibility. Sometimes you need visibility on what's that percent level hydrogen, if at all, for a loss of flame. So, good question. Does that answer the question, John?
I think so. Then there's I think a question Stuart wanted to ask. So Stuart, I'm going to try to unmute you and allow you to ask your question on the phone here. So you should have ability, Stuart, to unmute yourself and ask your question. Stuart Simmons.
Awesome. Yeah, thanks, John. Hey, thanks, Tim. Excellent presentation. Really loved it. It's brilliant. Hey, the question I have going forward, and it's one that we've been sort of raising ourselves, and I'm not sure you know, whether we've thought about it yet, but when we think about combustion control, as you sort of said, you know, we can still, no matter what happens going forward with the hydrogen introduction, we can resolve the set point of oxygen. We can resolve the safety issue, and I think in that regard, as you said there, the catalytic bead, even and the hot wires and the RTDs offer an advantage then, I guess, over lasers, because we can always see the hydrogen that comes through. But my question, and it's one I don't quite know how to answer myself, I haven't done it for years and years and years, Tim, is the wonderful thing about incomplete combustion when you're trying to generate CO2 is that you generate CO. So although you've still got enough oxygen, you don't have enough of it to complete your combustion cycle. So your oxygen readings can still be positive, but you're still in that, you know, in that bad, unfit zone. If I think about hydrogen going, sorry, long-winded question. If I think about hydrogen going forward, should we get to 100% hydrogen burn? How do we consider combustion control efficiency measurement if we only have hydrogen? Because then there is no sort of halfway point between complete and incomplete combustion. Do you have any thoughts on that, Tim?
Yeah, that's a great question. So so I'll go back to this slide right here just to kind of focus our attention and anchor our conversation. But from a pure hydrogen standpoint, the combustible measurement provides that ppm level measurement in case there were any hydrogen. So it's just more of a low level safety measurement when it comes to combustibles, if that makes sense, especially when you're using pure hydrogen. But what my biggest concern is when there's variability in the composition. That's where I become very concerned, because if you go from pure hydrogen to any high hydrogen blend, you immediately have the risk again of combustibles breakthrough, of potential ppm levels of carbon monoxide to indicate unsafe conditions. So when it comes to pure hydrogen, you know, you got that ppm level visibility for hydrogen safety, and then you got hydrocarbon detector for percent level measurements of hydrogen. When it comes to high hydrogen fuels, I still see the need for some type of combustible measurement, because you're going to want that visibility on whether or not you're close to combustible breakthrough.
Yeah, agree, Tim, 100%. So all the time that there is some hydrocarbon in there, then we can apply the same logic to not just the safety and the set point, but the efficiency point, your middle point, right? But if we trend towards 100% hydrogen, should we ever get there, then can you know, so your ppm breakthrough is safety, which I understand, that's great, but can we consider any way of doing an efficiency level, or do we need to look at it some other fashion then?
Yeah, that's an interesting question. And what's interesting about that is you start to rely even more on the excess oxygen measurement. And again, I keep saying excess oxygen because that's what's particularly unique about zirconium oxide, is it uses that excess oxygen measurement. So at that point, you're almost choosing your safety margin. If you're using pure hydrogen, so let me go back to pure. If you're using pure hydrogen, you're effectively choosing your safety margin. So your excess oxygen measurement would be indicative of, okay, you have 1% excess oxygen, meaning you have like that's, you know, 0 to 1% is your flexibility range. Then it becomes a layered question. Then it becomes a layered question on, is there a varying load requirement? Like, do you need to increase the firing rate higher? If you increase the firing rate higher, what does that mean? Does that mean that you need a 2% excess oxygen in order to have a safety window, or do you need 3%, 5%? Like, how much of a transition from lower operation mode to higher operation mode do you need to change your firing rate? So becomes a lot more when I think about pure hydrogen, I think a lot more about, like, what's that excess oxygen level going to be, and then having the combustible detector, having the hydrocarbon detector for the percent level measurements for safety effectively.
Right.
Yeah.
Hey, look, we'll take this on offline. I don't want to keep going, but it's something I'd like to chat to you about some more. But, you know, to me, that's sort of, you know, as we go forward, that's the big question we all have, I guess, is can we still sell the way we've always sold, which is, hey, you need an oxygen and you need a combustibles analyzer. You need the Thermox 5 because of all of these reasons. And I think it's easy to answer it for safety. I'm just not sure if I know how to answer it for efficiency anymore if we go pure hydrogen. Anyway.
Yeah, that's a good question. Yeah, from the efficiency standpoint, I mean, that's where high hydrogen blends come in because,
yeah, all the time it's blended. I think we're okay because we're still going to have that argument about CO and CO2, right?
Right.
Yeah. Anyway,
Yeah,
thanks. It was really good, Tim. Thank you so much.
Yeah, thanks for your question, Stuart. Yeah, but for anytime we talk about efficiency, having that secondary reference point, even if it's just hydrogen, it does provide that secondary measurement where you do have additional context for the specific application. So, but yeah, we could talk about it more offline. And if anybody else on this call would like to have additional conversation about this, these are important topics as we near the trend towards net zero emissions for CO2. These are important conversations to have, and I'm glad you brought it up. So feel free to reach out.
There's one other attendee, Mr. Jower has his hand up. I'm going to try to unmute as well, and if Mr. Jower's on, he can unmute his phone or computer and ask his question. We'll try that.
Yeah, hello. Can you hear me?
I can hear you. Yes, sir.
Yes, great. Actually, I joined a little late. I have one question. Let's say, I mean, we have a boilers, a furnaces running on fuel gas, mixed fuel gas from natural gas, also off gas from the plant. So how is it possible? Is it a straightforward? Just okay. If I could convince the management and we decide to go with replacing the fuel gas with hydrogen, is it as simple as changing the supply of fuel of the fuel gas? I mean, the type of fuel to be burned from fuel gas, which is methane rich, to hydrogen. Is it as simple as that, or it requires changes in all the setup in firing philosophy?
Yeah, so just going to the perspective. So when I think about moving from natural gas to hydrogen fuels, high hydrogen or hydrogen fuels in general, or pure hydrogen, I think it'd be really prudent to go through this list of potential risks because you want to make sure that the burner is designed appropriately to handle hydrogen. So whether that be reaching out to the burner manufacturer or burner manufacturer specific to hydrogen or hydrogen blends, I think that'd be really important because you want to make sure that it doesn't produce that it's staged, that the air is staged correctly so that you don't have too much thermal NOx generation, because there is a trade-off. When you start using pure hydrogen, you have the risk of potentially high thermal NOx. So it may be helpful just to have a review of the burner to make sure that the air is staged correctly enough. We're not going to get too significantly high thermal NOx. There's also some things like making sure that you have the right piping material so that stainless steel piping material, because carbon can face degradation over time. So you want to make sure that the piping material that you're using for your fuel, or if you have a separate line, are intact so that it can handle that type of changes in fuel. Because hydrogen is unique and it does have certain characteristics when you think about the piping as well. So I think it'd be prudent to have a review of your process to make sure that it can use hydrogen. But it's also possible that you could get away with it may be designed appropriately to use a high hydrogen blend as opposed to pure hydrogen. So I think it'd be prudent to get some type of consultation to make sure that it can handle it, but it's likely you'll be able to handle with at least a high hydrogen fuel blend without any major changes. Does that answer your question? Does that make sense?
Yeah, okay. Thank you for your elaboration.
Yeah, great question. That's important.
Oh, that's great. That was the last question, Tim, and appreciate the audience's participation there in the session. We're right at the top of the hour now, so I do want to thank Tim again. Thank you for presenting today and sharing your expertise. I do want to thank everyone on the call who stuck around for the hour and for attending today. I hope you found the content informative and educational. I just posted in the chat a few useful links on the products as well as local contacts. And as I mentioned at the beginning of the session, we are recording this and we will post it on the AMETEK Process Instruments YouTube page in the next few days, so you can review it or pass along to colleagues who perhaps weren't able to join today. So again, thank you everyone for your time. Thank you, Tim, for presenting, and hope everybody enjoys the remainder of your day. Thank you.
Thank you.